Welcome to my lesson on relative gravitational potential energy, often just called gravitational potential energy without the word relative. I put the word relative in because I believe it's more descriptive, especially when you're learning the concept. So let's see here. Now, the first thing I want you to realize is that you can't actually measure the actual absolute amount of potential energy an object has just sitting there. Um, Potential energy is always about changes in energy, like what happens when you raise an object up farther away from the Earth. It gains potential energy because it's attracted to the Earth. And if you lower the object down, it loses potential energy um, as it gets closer to the Earth. So yeah, the only thing you can actually measure is change in potential energy. And you may remember this formula from previous lessons. This is change in potential energy delta PE is equal to mg delta H. That's the mass of the object times the gravitational field strength, 9.8 newtons per kilogram, multiplied by the change in height, where up is positive. So this describes a change in potential energy. And I assert to you that it's really only changes you can measure. So let's imagine this. Why don't we imagine some object here sitting on a table of mass m, and let's just imagine that the table is, I don't know, 1 meter off the ground here, right? So you might say the object sitting on the table could fall down to the floor, so it would lose, mg, and then the height would be negative. The change in height would be -1 if it fell down to the ground, to the floor. So that's fine. But now I want you to imagine that we dig a hole beneath the object. Yes. So now the object can fall even deeper down to the ground, down to the floor, down to the bottom of this hole. Now, the question is, did digging that hole give that mass more energy? Did it do anything to that object? Did digging that hole change the object? And I would argue that it didn't do anything to the object at all. It just allowed another path for it to descend. And yes, it could fall down deeper, and when it fell down deeper, it would lose more potential energy. Yes. But I'm trying to explain the reason why we can't actually measure the absolute amount of this object, absolute amount of potential energy that that object has there sitting on the table, because you can't really define like how far it could fall. You can always dig a hole, like where does it stop? And the point is that it doesn't make any sense to assert that there's an absolute amount of potential energy that this mass has. Okay. But what we can do, however, is we can define something called relative potential energy. And relative potential energy is defining the potential energy of an object relative to some zero level, some zero height. So relative potential energy. Now, the formula for relative gravitational potential energy will be PE, the relative potential energy, is equal to mgh. And m is the mass of the object that is sitting there, and that could fall or rise. G is the gravitational field strength. It's positive, you note. Up is always positive, and this is always positive. And h is the height relative to some chosen reference height of the object. So, right, let's actually draw a line here, an axis, and see if we can explain this. All right, so arrow. So we'll draw a line down here. And this is going to be some y-axis, h-axis if you want, where up is always positive. So we're going to call up positive here. So up is the positive direction. By the way, you have to call up positive with gravity. If you call down positive with gravity, you're implying that gravity is a repulsive force. And last I checked, when I dropped the ball out of my hand, it didn't fall upwards. Gravity doesn't repel. Thus, you must always say up is positive with gravity. So what we've defined here is a y-axis or an h-axis. And in order to fix this axis, to define it properly, you need to define some level that is the zero height. So we're going to call that 0, h equals 0. You can really choose any height you want. It's kind of a matter of convenience, but I'll just place it there on this diagram. And then what this means then is that if you have an object above the h equals 0, here, let's see, we have some mass here, we'll call that m1. And if this object m1 here is above the h equals 0, this is called the reference height, by the way. Reference height. So if you have this object here, it's above the h equals 0 line, so that means that it has positive potential energy, right? Because it's above. And the h is positive, right? So this might be like 2 meters or 3 meters or something, but it's a positive number. Now, if you place the object here, this means, if this is like a second object, m2, the potential energy of this object would be 0, because it's at the 0 level, P equals 0. And you'll notice with the formula, right here, it's mg times the height relative to the reference height. So here, if the object is at this height, its height is 0, so it has 0 potential energy. And if you place this down here, another object, m3, then this object has a height which is negative, right? So the h would be some negative number, like -2, I don't know, times the mass times the 9.8. And so this would be, PE would be negative. That's my symbol for negative, PE. Yes? So the key act here is to choose that reference height. And again, the choice of that reference height is usually a matter of convenience. You put it somewhere that makes your life easier to solve a problem. Okay. So, and again, relative potential energy is potential energy relative to some chosen height. So there's the chosen height, the reference height. Okay. So what I'd like to do now is I'd like to get you to practice some problems with relative potential energy. So here's what we're going to do. In this picture, we have this 25 kilogram object teetering precariously on, I think it's the 10th floor. And I'm going to ask you to find the potential energy of that object relative to a number of different heights, different h equals 0s. All right, so let's see here. Red. So first off, why don't we put h equals 0 down there, okay? And I would like you to find the potential energy of this 25 kilogram red ball relative to h equals 0 down here. So I'd like you to press pause and do this problem, and then I'll do it after you turn the video on. So hit pause now, please. All right. So welcome back, and let's do this calculation. So the potential energy, now up is positive, and so the potential energy, the relative potential energy of this object is equal to mgh, and the mass is 25 kilograms. the gravitational field strength. We're on Earth, so it's 9.8 newtons for every kilogram. And the height. Well, the height is, if we imagine that this is a big giant y-axis where up is positive, and the 0 mark on that axis is down here, that means that this object is at the 30-meter mark. So the height in this is 30 meters. And so that is then equal to that is 7,350. Okay, so got that? That's good. So now what I'm going to do now is I'm going to change the reference height. And again, I'm going to ask you to find the relative potential energy relative to our new height. So why don't we put h equals 0 up there? Okay, so I would like you to find the relative potential energy of that mass relative to h equals 0 right there. So please press pause and do the problem on paper. And also you really should be drawing a diagram on the paper too. I find that will help you to learn this material a bit better if you draw it, okay? Every one of these little trial problems, I'd like you to try to draw a diagram, even if it's a crappy diagram, doesn't matter. And on that diagram also give the positive direction, right? Up is positive, and write the h equals 0 on your diagram. Okay, so please press pause now. Okay, welcome back. So now, with our new h equals 0 mark, our new coordinate system, such that it is, the PE is still equal to mgh, but now it is equal to the mass, again 25 kilograms, times 9.8 newtons for every kilogram, times the height change. But the height here, the object is now located at the 0 mark. And so we would put 0 meters right here. And so of course then that means the object has 0 joules of potential energy. So one thing you might be considering here, I've located the reference height at 2 different places. And I might ask the question, did the choice of your h equals 0 actually change the object? Did it give it more energy or less energy? Maybe think about that. So now let's try something else here. So I would like you to now find the potential energy, relative potential energy of the object relative to, and why don't we say this is relative to sea level. I know there's no ocean in here, but we can imagine it. And let's just say for ease of calculation that sea level is 80 meters below the object. Okay, so 80 meters below the object. Sorry about that little glitch. So 80 meters below the object. Okay. So, yeah, please press pause, draw a diagram for it on your own paper, and find the potential energy. Go. All right, welcome back. So let's draw a diagram here. Doesn't have to be a good diagram. So here is the building and the mass right there, and there's the ground, and then we're on a hill, which we are, and there is sea level, and sea level will be h equals 0. And so then the object's height is like that, and relative to sea level, this is 80 meters below. So we imagine this axis here, this imaginary vertical h-axis, and the 0 is here, up is positive, so the object's height is now positive 80 meters. So mgh, and so that is equal to 25, 9.8. That's infuriating. I'm sorry about these glitches, folks. Mac is letting me down. 9.8, and then the height is 80 meters. 80 meters. So 25. So that would be 19,600. 19,600 joules. Yes? So, okay, so it's quite a bit more. But then I ask you again, did that choice of h equals 0 actually give the mass more energy? Consider that. So now let's go into the final trial here, which is the most interesting one, I think. Now, normally we choose h equals 0 in a convenient place, and maybe bottom of the building was convenient, or maybe the top of the building was convenient. I don't know. Sea level seems a little weird. But just for the sake of a thought experiment, why don't we try this? Why don't we say we want to find the potential energy of the object relative to the... This is getting ridiculous. Yeah. Macs are irritating sometimes. So relative to... Really? Yes, no? This is designed to... relative to the top of Mount Everest. $88.48 meters above sea level. And I'll remind you, the object, really, is 80 meters above sea level. Okay, give it a go. Press pause, draw a diagram. Yes, a diagram with Mount Everest but beside this building. I know we're in Vancouver, but just draw a little diagram, okay? Press pause and give it a try. Go. Okay, welcome back. So I'll show you my diagram. This won't be much of a diagram, but there's supposedly Mount Everest. So there. And this here is h equals 0. And there's our little icon for sea level. And then we are on a bit of a hill, obviously not to scale. And there's the object right there. So Everest is 88.48 meters above the sea. And then this is, I'm not going to record this video again because it is a lot of effort. It won't come back. So here, this is getting ridiculous. Is this Mac trying to force me to buy an iPad Pro? Am I making this impossible? So here, well, actually, that wasn't what I meant. This here is 80 meters that way. And so what we can do then, we can go 88, 48, and then, so that would be 87, 68 meters. From the top of Mount Everest to the block. And so the potential energy is equal to mgh. This is comedic. That is equal to mgh, which is equal to the mass, which is 25 times 9.8. But what's the height? Well, you see h equals 0 is on the top of Mount Everest, so we are below h equals 0, we're up as positive, so this would be negative 8768 meters. Interesting. Negative. Okay. So we go. And so that would be, I think I need scientific notation here, 2.1415 times 10 to the power of, that would be 6 joules. Okay, negative. So it's negative 2.15 million joules. Interesting. Okay. So, and that, again, I asked you the question, does our choice of h equals 0 actually change that mass just sitting right there? It's just sitting right there, not dropping, not doing anything. But I chose h equals 0 to a number of different places. Did that choice change that object? And I would say no, because otherwise we would be saying that my thoughts, my choices would actually change the physical state of an object, and that's almost implying telekinesis. My thoughts can't change that object. All we're doing is we're changing how we measure the potential energy, where we measure the potential energy from. That is it. It is purely an arbitrary choice. Okay? So, yeah. Now, I ask you another question. How about this? What if I chose Mount Everest as the ultimate reference frame? What if there was some decree that said that you have to choose Mount Everest as your reference frame? What would that mean about the potential energies of all objects on the surface of the Earth, right? You know, really, we could do this. We could say that h equals 0 is on the top of Mount Everest. I mean, I've just said that your choice of h equals 0 doesn't actually change the object, right? It doesn't really matter. It's just a matter of convenience. Maybe this isn't so convenient. But if I chose h equals 0 on the top of Mount Everest, what would it mean about the potential energies of everything on the surface of the Earth? Think about it. Press pause if you want. Okay. So I would say that if h equals 0 was on top of Mount Everest, that would mean that the potential energies of all objects on the surface of the Earth would be negative. Huh. That's interesting. So would it matter? No. It wouldn't change the object. I mean, if the object were to drop from that 10th floor down to the ground, it would still lose the same amount of potential energy, whether we chose h equals 0 on the ground or on the floor that the ball object is at, or on the top of Mount Everest. It would be the same. So the choice of h equals 0 doesn't matter in that regard. So if you chose h equals 0 at the top of Mount Everest, everything would have negative potential energy on the Earth. So there. I kind of asked my question already. Well, here. Okay, they'd all be negative. Now, I asked this question because it goes towards physics 12, and it's a kind of a subtle thing. What we do in physics 12 is we choose h equals 0. If we're doing, this is for space problems, by the way, like we want to raise the potential energy of an object. We want to raise an object from the surface of the Earth up to like 400 kilometers to the height of the space station. We can't use mg delta h anymore, so we have to choose a different reference frame. And that reference frame we choose is not at Mount Everest, not on the top of Mount Everest, but higher. It actually is higher than Mount Everest, higher than the space station. So h equals 0. Imagine it moving up above the space station, but higher than that still. We move h equals 0 higher than Mount Everest, farther than Mount Everest to the moon, maybe, but farther than the moon, farther than the sun from the moon, from the Earth, farther than the center of our galaxy to the Earth. What we say, never mind, why would we do that? Well, we do that for problems that you do in space. But if you put h equals, what we do is we put h equals 0 higher than Mount Everest, very far away. We put it at infinity. And then we end up using this formula for potential energy. All right, so the potential energy you use in grade 12 is, for space problems at least, is this. And this is the gravitational field constant, the universal gravitational constant. This is the mass of the Earth. That's the mass of the thing you're lifting. And that's the distance from the center of the Earth. But notice that negative. Notice that negative. Look at that. Important. Right? What that negative means is that in this reference frame, all potential energies are negative. Because what we're doing is we're putting h equals 0 at infinity, which isn't really a place, but just imagine any distance you can, and infinity is farther. Okay? It doesn't really end. So that's something for grade 12, and I just wanted to mention it to you now. You don't have to know it right now in physics 11, but maybe later. And thanks for listening. I'm sorry about the technical glitches there. This Mac is, kind of irritating, especially since it works 90% of the time, and it glitches out. But thanks for listening, and hopefully this is helpful. Take care. Bye-bye.